Today, we will introduce the optimizing impression counts for outdoor advertising problem. The outdoor advertising market reached $30 billion last year. More than 80% of drivers will notice billboards during travels. The question is, how do we improve the effectiveness of the advertisement? To address this question, we introduce the impression counts for outdoor advertising problem. Given a trajectory database, a billboard database, and a budget, we aim to find the optimal deployment strategy which maximizes the overall advertising influence. Before explaining how to find the optimal strategy, the first challenge is how to measure the advertising influence to an audience. Assume a driving car meets a billboard. Each billboard has an influence range. When the driver is in the range, we say this driver is impressed. But is it enough to impress a person only one time? It's a big no. We will use the following example to explain. It is hard to remember a billboard by only one-time notice. But we can deepen the impression by showing the same advertisement multiple times. Eventually, this driver will remember our advertisement. Now, we know the influence increases when the impression times increase. Moreover, the logistic function should be considered as it widely used to measure the advertisement influence. But like a great man once said, no two leaves are alike. For the people who are easily impressed, only a few times of advertising can change their mind. For others who are stubborn, we need more advertising to influence them. By utilizing the logistic function, we can measure advertising effectiveness. But the logistic function leads to two challenges. First, the influence model is not submodular, which means that any greedy-based algorithm is not applicable. Second, our problem is NP-hard. To conquer these challenges, we introduce the upper bound estimation and branch and bound framework. For the upper bound estimation, we use a tangent line that intersects with the logistic S-curve. The red line is the upper bound influence. The logistic function measures the lower bound influence. By using the upper bound influence, the model becomes submodular. Based on the estimation function, we can calculate the upper bound and lower bound of each strategy. And we know that the lower bound is always lower or equal than the upper bound. Therefore, when we compare two strategies, if the upper bound of strategy 2 is lower than the lower bound of strategy 1, we know that 1 is better. For the branch and bound framework, think of each strategy as a branch. We explore each branch by considering a different combination of billboards. For those who have small upper bound influence, we will prune it. For the branches having an ideal upper bound, we explore them further. The searching process will terminate until finding the solution. For further optimizing our framework, we introduce the progressive bound estimation. With slight worse effectiveness, it hugely improves the efficiency compared with the original version. We also prove that both of them can achieve an approximation ratio. If you are interested in our research, please read our paper in KDD 2019. Thank you.